So this is a topic where, have you heard about the structures as H2, H2S2O7, H2S2O8, H4SP2O7, H4P2O8, H2S2O5, H2S4O6? Like there are many kind of formulas are there and structures are there. But the thing is, uh, and nomenclature is also there. Like along with the structure, we have to know the name of these compounds also. Like some compounds are known as pyrophosphoric acid, pyrosulfuric acid, peroxysulfuric acid, and then hypopyrosulfuric acid. Kind of confusing. Like it will be confusing for you. And the thing is, this is a topic which is important. Oxy acid. So we'll be doing it very systematically, and we'll be able to understand it completely. Right. So in oxy acid, what are oxy acid? First thing is, what are oxy acids? When the non-metal is bonded with OH group, then the compounds are known as oxy acids. Right? You are very familiar with oxy acids. I'll be giving you the examples. Non-metal is bonded with OH group. These are known as oxy acids. Obviously, no one is going to ask the definition, but we should be clear about it. Non-metal. Sir, what are the examples? H2SO4 here. H2SO4 is like this. H2SO4 is what? H2SO4 is oxy acid, sir. Because sulfur is bonded with OH. Sir, how we know that sulfur is bonded with OH? So the thing is, we should know how to draw the structure. Like here, I am teaching you how to draw the structure of oxy acids, right? So many oxy acids we can write. S3PO4, H2CO3, S3PO3, HNO3, HNO2, S3PO3, S3PO2. We will be seeing the naming later. But first, what we are doing, beta? First, we are seeing how to draw the structure, right? We are completing this thing. So I'm telling you one thing, one very important line which is helping you, which will be helping you in the drawing structure. So when hydrogen and oxygen both are there, hydrogen and oxygen, hydrogen and oxygen both are there, then there will be a bond found by OH always. Like central atom is there, side atom, inside atom, hydrogen and oxygen both are there, then you have to make a bond of OH. Like OH, O and H you will be connecting. Okay, let us see how to draw the structure. For example, we are talking about H2SO4. So central atom is sulfur, and then two hydrogen and four oxygen are there. So two OH we can make. Oxygen will be making how many bond? Two. So one bond is made by hydrogen, then only one bond it can make. Right, in this way. Now two oxygens are remaining. So one oxygen will be making double bond, one oxygen will be making double bond. So now ask sulfur, can you make six bond? Yes, I can make six bond because sulfur has six valence electrons and it is belonging to third period. Third period can expand its octet, means as many number of electrons are there in the valence shell, third period element and onwards can make that number of bonds because they can unpair the electron, right? Six electrons are there total in the valence shell. So as many number of unpaired electrons are there, that many number of bond can be formed. But suppose the electrons are paired. For example, like sulfur is 3s2, 3p4. So we can write it like this. So because of availability of 3D, this electron can be excited, this electron can be excited. So 6 bond can be formed. Okay. S3PO4, central atom will be phosphorus, right? And hydrogen, we can see as 3, 4 oxygen also I can see. So now, how many OH bond will be there here? OH bond will be there as 3. So let us make 3 OH bond and then double bond O. One very important point. When you are drawing the oxyacid of phosphorus, I'm writing it here. In oxy acids of phosphorus, P double bond O must be present. In oxyacid of phosphorus, P double bond O must be present. For example, let us just try this one here. S3PO2. When we are drawing the structure of this one, so central atom is phosphorus. So whenever you are drawing oxyacid of phosphorus, first you make P double bond. Otherwise, what you will be doing, you are seeing 3 hydrogen, 2 oxygen. So you'll be making 2 OH bond. That will be a wrong structure. I'll be telling you reason later. But in the case of phosphorus, you have to make P double bond. Okay. Now you see, 1 oxygen is remaining, 3 hydrogen. So only 1 OH bond can be formed. Right. Sir, now 2 hydrogens are still remaining. What to do? You just make bond direct with the phosphorus. You just make bond of hydrogen direct with the phosphorus, right? In this way we can make. Okay, now you try all the structure in your notebook. H2CO3, S3PO3, all these structure, you try all these in your notebook. Okay, let us see. Have you made? Afik? Done?
Yes, sir.
Varun?
Yes, sir.
Vibani?
Yes, sir.
Ruba?
There are only few structures needed.
So H2CO3, if we make, then carbon is the central atom. Central atom will be carbon, and we can see 2 hydrogen and 3 oxygens are there. So 2 OH bond will be there, 2 OH bond. And then there is 1 oxygen is still remaining, so it will be making double bond O. S3BO3, boron is the central atom, right? And 3 hydrogen, 3 oxygen. Okay. So 3 OH bond will be there. Fine. HNO3. HNO3. How to make this one? Nitrogen is the central atom, 1 hydrogen and 3 oxygen. So 1 OH bond is there. Okay, now it is important. 2 oxygens are there. Like we have done it here. We have done it. Chemical bonding in the starting classes, we have done it. 2 oxygens are there. Now, like oxygen wants to make how many bonds? Double bond. But if we make double bond, then nitrogen will be having total 5 bonds, which is not possible because it is a second period element. It can make maximum bond 4. So, one double bond will be making, and now another bond will be making as a coordinate bond, right? If you remember, like nitrogen has a pair of electron, so we'll be making a coordinate bond. Octet of both the atom is completed in this way. Oxygen was having 6 electron. By making a coordinate bond, now it is having 8 electron. So its octet is completed now. And nitrogen octet is also completed, right? HNO2, very simple. HNO2, nitrogen is the central atom. There is one OH bond and one double bond O, and then one lone pair will be as it is. S3PO3, phosphorus is the central atom, and double bond O we must have to make, right? Double bond O will be making, and then we can see 3 hydrogen and 2 oxygens are there. So OH, and 1 hydrogen will be there, right? Have you understood it here, everyone?
Yes,
Yes,
sir.
sir.
All the structures were correct? Okay. So now the thing is, these are the cases where there was only one central atom, right? And before going onto the two central atom case, we can see a term which is basicity. 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 What is basicity? So, like First, the thing is these are acids. Why they are acids, sir? Because hydrogen is connected with more electronegative atom. When they are placed in the aqueous solution, they will be losing the H plus. And you can see in every case, like when the H plus is released, negative charge will be formed. And that negative charge is stable in all the cases because of resonance. In all the cases, negative charge will be doing resonance, right? Because double bond O is there. So that is why they are acids, right? And the another thing is, like if you can ask me, sir, there is no double bond, but the thing is better when you are having a negative charge here, phosphorus has a vacant orbital. Boron has a vacant orbital. Boron used only 3 orbital. One orbital is still there, which is vacant. So it can accept the electron in the vacant orbital. That is also resonance. That is also resonance. Okay. So yes, so these are acids. They can lose H plus in the aqueous solution. So what is basicity, sir? If they are acids, then we should represent acidity for them. Why basicity? Because for H2SO4, we will be saying that its basicity is 2. H2SO4 basicity is 2. What does it mean? It means when you are having a base, so 2 bases or 2 mole of base are required to remove H plus from H2SO4. 2 mole of base are required to remove H plus from H2SO4 because there are 2 H plus. This is why we are using basicity. Like acid will be losing H plus, but it can lose H plus when someone is there to accept H plus. And the one which is accepting the H plus is known as base, right? So what does the basicity means? How many bases are there to take the H plus? So how many bases are there? For H2SO4, number of bases required is 2, right? So to find the basicity, we just have to check how many hydrogens are connected with oxygen. That is simply the basicity is. How many hydrogens are connected with oxygen? That is the basicity. So for H2SO4, the basicity is 2. S3PO4, 3. H2CO3, 2. S3BO3, no. For S3BO3, it is not 3. S3BO3 is not 3, it is 1. HNO3, it is 1. HNO2, it is 1. S3PO3, it is 2. H3PO2, it is 1. Like in most of the cases, what is the basicity? The hydrogen which are connected with oxygen, that number is the basicity, right? Because those are the acidic hydrogens. Like if we see here, in this case, hydrogen is connected with phosphorus. That is not acidic hydrogen. That cannot be removed, right? But this hydrogen can be removed because it will be doing resonance, and it won't be doing resonance if you remove hydrogen this from here. So basicity is what? Hydrogens which are connected with oxygen directly. In the case of S3BO3, it is not 3, it is 1 that I'll be teaching you. Right. Okay. So I think that we can take now only. Otherwise, you will be thinking, sir, why the basicity in the case of S3BO3 is not 3. Okay. So the thing is, how the basicity is defined. When a acid is taken in the aqueous solution, it will remove the H plus, right? That is known as the basicity. But the thing is, it has a vacant orbital. We know that. And vacant orbital means it is having 6 electron in the valence shell. So its octet is also not completed. Incomplete octet it is having. Incomplete octet it is having. So if the octet is incomplete, that means whenever this is put into the aqueous solution or with water, it will be accepting the lone pair from water. It will be accepting the lone pair from water. Okay. It will be accepting the lone pair from water because, one thing was there, Lewis acid, Lewis base. One which can accept lone pair, Lewis acid. One which can donate lone pair, Lewis base. Lone pair accept, lone pair donate. So BH3BO3 is acting as a Lewis acid here. because it is accepting the lone pair, right? So what will be making B OH 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 OH2, and there will be coordinate bond. This we have seen here, coordinate bond formation. Oxygen has lone pair, boron has vacant orbital. So there will be a coordinate bond formation takes place. And we know in the coordinate bond, if we remove the arrow, if we remove the arrow, if we remove the arrow, there will be a positive charge formation takes place, right? On boron, there is a negative charge formation takes place. Fine, right? Okay. So now the thing is, this OH2 plus, this wants to lose its H plus again. Why? Because it is having a positive charge, it wants to be neutral. So how to be neutral? How it can be neutral? OH, OH. Like if it takes a electron from any bond, it will become neutral. So B, OH, 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 and OH negative, and one H plus is released. What I'm what we have done here, let's see again. Oxygen has a positive charge. So oxygen wants to be neutral. How it can be neutral? If it take electron from any of the bond, right? So if it take electron from this bond, then like this will be the reactant again, reactant. But if it take electron from this bond, then like it will become neutral and H plus will release, right? Yes, H plus will release. So you can see in the overall case, only one H plus is released. That is why the basicity is coming as 1. Basicity is actually not the hydrogen which are connected with oxygen. Basicity is number of hydrogen which are released when the compound is placed in aqueous solution, right? But generally, in most of the cases, the hydrogen which are connected with oxygen all will released, except one case, that is S3BO3, right? Except one case. So except S3BO3, in all the cases, hydrogen which are connected with oxygen, that is the basicity. For S3BO3, basicity is 1. Why 1? Because when we place it into the water, it will be accepting the lone pair because it is electron deficient. And then it will not be losing these H plus, it will be losing this H plus, right? So its basicity is coming as 1. Have you understood up to here?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay. Okay, fine. So now we can see the cases where there is more than one central atom, right? More than one central atom is present. So when more than one central atom is present, then what will happen here? Let us see. What you have to do then in that case, find the oxidation state. Find oxidation state of central atom. If oxidation state is more than maximum oxidation state, then peroxy linkage. Peroxy linkage means this one. This is peroxy linkage. Oxidation state is less than, sorry, equal to maximum oxidation state, then oxy linkage. Oxy linkage means linkage like this. If oxidation state is less than maximum oxidation state, then direct linkage. Now, what is this case? So we have to, we will be like, this is very, very simple, right? If I'm taking one example, then you will be able to understand. So I'm taking one example here. It's H4P2O8. I'm taking O8. Okay, this will be given to you. So the thing is, we have to draw its structure. So how to draw the structure? So first we have to find the oxidation state of phosphorus. How to find the oxidation state of phosphorus here? How to find this? At least we are knowing this now. Hydrogen has +1 charge. So +4 plus. Let us assume the oxidation state of phosphorus is X. 2 phosphorus means 2X. Oxygen has -2, so -16 is equals to 0. So value of X is coming as +6. Now, +6 is the oxidation state coming. You have to compare this with the maximum oxidation state of phosphorus. So for phosphorus, the maximum oxidation state is +5 because it has only 5 electrons in the valence shell. Here, what is the maximum oxidation state? Like as many number of electrons are present in the valence shell, only that can be lost now. Only that electron can be lost. So if phosphorus has 5 electron in the valence shell, so oxidation state maximum can be +5. It cannot be +6. So by here we can see oxidation state is coming more than maximum. Then we have to make a peroxy linkage. So peroxy linkage will be between phosphorus and phosphorus. So how to draw the structure? Phosphorus, oxygen, phosphorus. Okay, this is done. Now, how many hydrogens are there? 4. How many oxygens are there still? 6. But I told you, in the oxyacid of phosphorus, we always have to make P double bond. Okay, so P double bond will be formed. Now, how many hydrogens are remaining? 4. Oxygen, 4. No problem. Let us have 2 OH with both the phosphorus atom. And we try to make the structure symmetrical. We have to try to make the structure symmetrical. And phosphorus can make 5 bond. So yes, so that is the correct structure of this molecule, right? Have you understood this one, everyone?
Yes, sir.
Varun, Afik, Ruba?
Yes, sir.
Okay, so now you try these cases. H4P2O7, H2, S2O7, H2, S2O8. Okay, try all these 3 cases here. H4P2O7, have you made it?
Yes, sir.
Yes, sir.
Okay. So first we'll be finding the oxidation state, which is coming as +5, right? So it is +5 means it is equal to maximum. So we'll be having oxy linkage like this. P double bond O we have to make, and then 4 oxygen and 4 hydrogens are there. So we'll be making bond with the OH. Have you understood? Like you made the same?
Yes, sir.
Afik,
Yes, sir.
Varun,
Yes, sir.
Ruba?
Yes, sir.
Okay, very good. H2S2O7, sulfur is having the oxidation state as +6, and now sulfur, sulfur, oxygen, oxygen. Like this will be making, because, wait. It is +6. So it is equal to maximum. Sulfur has 6 valence electron. So it is maximum only. So oxygen, sulfur. Now 2 hydrogen are there and 6 oxygen are there. So 1 OH, 1 OH. Now 4 oxygen are still there. So double bond O, double bond O, double bond O, double bond. Right. So this is what we can see here. This will be the structure. Did you make the same structure, Afik?
Yes, sir.
Varun,
Yes, sir.
Ani, Ruba?
Yes,
Yes,
sir.
sir.
Very good, yeah. In the next case, this is having plus 7. 16, 14 plus 7, right? Which is coming more than maximum. So more than maximum means peroxy linkage. So this is the correct structure. So this is also correct.
Yes, sir. Yes, sir.
Okay, very
Yes.
very good. So
Yes.
now the thing is, one question is that how the question will be asked from these cases, in which of the following cases, like integer type question, in which of the following cases oxy linkage is present, in which of the following cases peroxy linkage is present, like that. Okay, fine. So now one thing which I wanted to tell you here is that, like the oxidation state, if they ask you, if they this question is asked, what is the actual oxidation state of phosphorus here? So answer is not +6 here. Answer is not +6, because maximum oxidation state, like more than maximum oxidation state, is not possible. Like +6 is coming, but by formula it is coming now. How to see the oxidation state? Actually, how to see the oxidation state? What is the correct way? You see the structure. You know what is the oxidation state? Covalent bond you can see. If you assume all the covalent bonds as ionic, then atom having the charge is known as the oxidation state. Didn't understand? Listen it again. The covalent bond, what the atom is making, if we assume those covalent bond as ionic, then atom, whatever the charge is carrying, that charge is known as the oxidation state. For example, HF is there. So if we break this bond, we will be having positive charge on hydrogen, negative charge on fluorine, because fluorine is more electronegative. So we have to convert this covalent bond into ionic. Ionic means charges will be there. So less electronegative will be having positive, more electronegative will be having positive. So here oxidation state of hydrogen is +1, fluorine is -1. That is why we mostly assume the oxidation state of hydrogen is +1, because the bond is breaking, hydrogen will be having +1 charge. Now in these cases, you can see phosphorus is having total 5 bond only with the oxygen. Oxygen is more electronegative. Oxygen is second most electronegative atom. So when we break these bonds, phosphorus is having +5 charge. How many charge? How much charge? +5. So sir, what is this? Like, oh, confused. What is this, yaar, chemistry? Huh? Here, like we are finding +6. This is +5. What actually it is? So the thing is, what the mistake here in formula we have done, beta. In this case, we have assumed the oxidation state of oxygen -2, right? Oxygen oxidation state, you are assuming -2, but in reality, one oxygen and this one oxygen, they are not -2, they are -1 actually. They are -1. You can see this oxygen is making one bond with phosphorus, but one bond with oxygen only. So oxygen-oxygen bond, there is no En difference. So if we break this bond, no charge will be coming on the oxygen. If we break this bond, so only -1 will be coming. So oxygen, we assumed oxygen is having -2. So generally it has -2. That is why we assumed -2. But in reality, they are having -1. So, but like if you, in this formula only, if you take 6 oxygen as -2 and 2 oxygen as -1, So the answer will be coming as correct only, right? So then we are using it reverse. When we are finding the oxidation state and it is coming more than maximum, that means that is the wrong oxidation state. That means we have assumed oxygen as -2, all the oxygen as -2, that is wrong. Some oxygens are -1, that means peroxy linkage is there, right? This is how this trick is made. This is how this trick is made, right? Oxidation state cannot be more than maximum, but oxygen can have less than maximum. It will be -1 or it will be having peroxy linkage. Have you understood it now, everyone? Hello?
Yes, sir. Yes, sir.
Like why, how we are using this thing? Okay, so now two more acids are there, H4P2O5, H4P2O6. H4P2O5, H4P2O6. So in these cases, beta, in these two cases, we have to make the structure. But the point is, like these are two important one, because the thing is that is the trick, that is not the rule. Actually, the structure, the in the way they are existing, they are existing. We are trying to remember them. So that is how why we are using these particular tricks, right? But they are not rules, right? So H4P2O5 structure, how it is existing, let us see. Oxidation state of phosphorus, if you find, so that is coming as 10, 10 minus 4, 6, 6 divided by 2, 3. So oxidation state is coming less than maximum. Maximum is 5, it is coming less than maximum. So the linkage should be direct, like it should be like this. But the point is, it is having a oxy linkage. It is having a oxy linkage. H4P2O5 is having oxy linkage. If we know this, then drawing the structure is very easy. P double bond we have to make. Now we can see 4 hydrogen, 2 oxygens are there. 1 OH, 1 OH. 1 hydrogen, 1 hydrogen. Yes, correct. Okay. Like the thing is, we just have to remember that it has a POP linkage here. It has a POP linkage. It has a oxy linkage. It has a oxy linkage. That's it. If they ask you what is the basicity here, so we can simply see the structure and then we can see 2 hydrogens are connected with oxygen. So basicity is 2. Correct. H4P2O6. If you find the oxidation state here, so 12, 4, 8, 8 divided by 2, 4. So it is coming as +4. So +4 is the oxidation state, that means less than maximum. Again, direct linkage. But its two structure are existing. One where oxy linkage is there, POP. How many hydrogens are there? 4. How many oxygens are there? 3. So it cannot be a symmetrical structure. 2 OH will be with 1 phosphorus, 1 OH will be with another, and 1 hydrogen will be like that. Okay. So that's the structure here. We can see. Then H4P2O7. Sorry. One structure is this where POP linkage is there. But we can see oxidation state is not maximum, it is less than maximum. So direct linkage, the structure which is having direct linkage also exists for this case. Okay. So P double bond O, P double bond O. How many hydrogen? How many oxygen? 4 and 4. So 4 OH bond. 2 OH bond with each phosphorus. Okay. So that is the structure will be existing, PP linkage. Like both the structure exist here. For H4P2O6, two structure exist. One POP linkage, one PP linkage. Now the point is, if the question is asked, I'm asking the question, which of the following must have oxylinkage. Must have. And if this option is given, then we will not count it. Because it must not have, it may have. There are two structures. No? But if the question is asked, which of the following cases oxylinkage may be or oxylinkage is present? So yes, oxylinkage is present. But oxylinkage is always present? No. Oxylinkage cannot be present. It is also true. Have you understood here this case? These two cases, will you remember? H4P2O5, H4P2O6.
Yes, sir.
Okay, sir.
Yes.
Very good. The question can be asked in this way also. Just see, listen the question. Is there any oxylinkage in H4P2O6 where basicity is 3? So yes, if the basicity is 3, then POP linkage is there. If the basicity is 4, then PP linkage is there. Right? Okay. So one more structure. H2S2O3. H2S2. You try this one. You try this one by yourself. H2S2O3. H2S2O3. Oxidation state is coming at 6, 4 plus 2, which is very, very less than maximum. So direct linkage. Okay. So the thing is here, when we are trying this structure, central atom is sulfur, and we can see there are 2 hydrogen. So 2 OH bond we can make. 2 OH bond we can make. Now, 1 oxygen and 1 sulfur is there. So oxygen will be making double bond and sulfur will also be making double bond because sulfur also belong to the oxygen family. So we will be making bond with this in this way. And you know better, like this is just the structure of H2SO4. Like it is made from H2SO4. What is H2SO4? Sulfuric acid. When we remove one oxygen from sulfuric acid and we add one sulfur instead of that, so we'll be having H2S2O3. Right? You removed one oxygen from sulfuric acid and on the place of that you added sulfur. So this will be the structure. And we know how the H2SO4 looks like. This is how the H2SO4 looks like. So you just have to remove oxygen and you have to put the sulfur. That's it. And when you are removing oxygen and adding the sulfur, the name become thio. Thio word will be coming. So its name is thiosulfuric acid. Because you removed oxygen and you added sulfur, so the name will be becoming thiosulfuric acid. Okay. You can tell me,
Yeah, do.
huh?
We'll remind you from next time.
Phosphoric, phosphorus. Phosphoric, phosphorus acid. And then if we remove one oxygen from here, then it will be forming S3PO2. What is S3PO2? Hypophosphorus. S3PO2 is known as hypophosphorus. S3PO2 is known as hypophosphorus acid, right? And we are able to draw the structure, right? How the question will be asked? What is the oxidation state of phosphorus in hypophosphorus acid? Or what is the basicity in hypophosphorus acid? So we should know what is hypophosphorus, right? So it is derived from phosphorus. When one oxygen is removed, then the resulting oxy acid will be known as hypophosphorus acid. Now, again, it is not necessary that every oxy acid will be generating hypophosphorus acid. For example, sulfuric acid is what? H2SO4. Sulfurous, H2SO3. Now, there is nothing like H2SO2. H2SO2 does not exist. So there is no hyposulfurous acid. Okay. Like we are having name for the compounds what are existing. We are not doing IUPAC nomenclature here. We are not doing IUPAC nomenclature. Whatever the oxy acid already existing, there are names and we are learning their names, right? So they will not ask the name for any compound. Like they will be asking the name of existing compound only. So next we can have HNO3. HNO3 is nitric because nitrogen is present in +5 oxidation state. Then if we remove one oxygen, it will become nitrous. This is nitrous acid. Clear? Fine, sir. And then if we remove one oxygen from here, then the compound which is formed is HNO. But you know, HNO does not exist. HNO does not exist. So, sir, why we are taking then? Its dimer exists. Dimer of HNO exists, which is known as H2N2O2. Right? This is dimer of HNO. And this is known as hyponitrous acid. This is known as hyponitrous acid. And if we want to draw the structure, so there is nitrogen and nitrogen, there will be a double bond, and there are two oxygen and two hydrogen. So just make one OH. Right. So as you can see, nitrogen is having 3 bond and it is symmetrical structure. So this will be the structure for H2N2O2. It is hyponitrous acid. So only 2 hypous acid are there. There is no hyposulfurous. There is no hypocarbonous because even carbonous is not there. So there are 2 hypous acid. Okay. So this is the case A where we'll be using hypo. Now second case, case B. From pyroic acid, if you remove one oxygen, then the resulting oxy acid will be called as hypopyroic acid. Okay. Hypopyroic acid. I'll be asking you the name in the last. Let us see who has sharp memory. Hypopyroic acid. Right? So this is like from pyroic acid, we are removing one oxygen. Resulting oxy acid will be known as hypopyroic acid. For example, let us take the example. What was pyro? H4P2O7. This was pyro air. And this was pyrophosphoric acid, right? And suppose a compound is given, then like, you know, one thing I can tell you very important is that when there are 7 oxygen, 7, it is always pyro, right? And there are 2 cases where oxygen 7 are present, H4P2O7, H2S2O7. So pyrophosphoric, pyrosulfuric. So like the thing is, we do not need to always start it from the basic, from ic acid, then twice, then water. You can remember it here. When there are 7 oxygen, it will be pyro, right? So it is pyrophosphoric because it is phosphorus. When there is sulfur, it is pyrosulfuric, right? Okay. So this is what, this is pyrophosphoric acid. This is pyrophosphoric acid. Pyrophosphoric acid. Now, if we remove oxygen from here, what it will be having? It will be becoming H4P2O6. Now, H4P2O6, its name will be hypopyrophosphoric acid. Hypopyrophosphoric acid. Simple. It's very simple, right? So this is second use of hypo, right? From pyroic acid, if we are removing one oxygen, resulting will be known as hypopyroic acid. Okay. So this was about hypo. Now third is known as peroxy or per prefix. Third. Peroxy acid or peric acid. When this will be using here? Peroxy means when peroxy linkage is there. And you remember when we used to find the peroxy linkage, when the oxidation state is maximum. And when we are having maximum oxidation state in the ic acid. So in the ic acid, if you are having additional oxygen, like one more oxygen is there, then the resulting oxy acid will be called as peroxy acid, or we can call it peroxyic acid or peric acid. Peric acid. Example. Let us take the example. For example, we are having HNO3. What is HNO3 here? HNO3 is nitric acid. Okay. And if we are adding one oxygen in that, what it will be having? It will be making HNO4. Right. And what is the oxidation state of nitrogen here? You can see it is +7, which is not possible, which is not true. It is coming +7, like it has 5 electron in the valence shell. How it can lose 7 electron here? It is not possible. Practically, it is not possible, right? It is coming as +7 because we are considering all the oxygen as -2. But all oxygens are not -2 because +7 is not possible, right? So we can say nitrogen will be the central atom, one will be OH. And now how to make the peroxy linkage? Sir, when we are having two central atom, then what we do, we make peroxy linkage in between those central atom. For example, H2S2 is there. We will be making peroxy linkage between sulfur and sulfur. When we are having H4P2O7, we will be making peroxy linkage in P and P. Now, where we are having the peroxy linkage? Between two different atoms here. Nitrogen and another one is hydrogen, right? So between nitrogen and hydrogen, you will be having peroxy linkage, right? In this way. And now how many oxygens are still there? Two. So one will be double bond O, and nitrogen will make fourth bond as coordinate. We know this, right? Fourth bond will be a coordinate bond. So like if you just see here, what was HNO3? HNO3 was this one. So what we did, we just changed this OH to OOH, right? OOH. This is a peroxy linkage. Okay. And if someone is asking, what is the oxidation state of this nitrogen? So our answer will be +5 because it cannot go beyond +5. Now, how sir it is +5? 2 bond, 1 bond, 3 bond. So when you will be breaking these 3 bond, nitrogen will be having +3 because nitrogen is less electronegative, oxygen is more electronegative. And in this bond, 2 electrons are of nitrogen only. So when you are breaking this bond, nitrogen will be having +2 because oxygen is more electronegative. Oxygen is going to take the bonded electron and both the electron are of nitrogen. So +2 from here, +3 from here. Overall, it will be +5 only, right? Okay. So this is what is the name of this? This is known as peroxynitric acid. Peroxynitric acid. Similarly, H2SO5, H2SO5. H2SO4 is, what is H2SO4? Sulfuric. If we are having one oxygen extra, it will be becoming H2SO5. And what is H2SO5? Peroxy sulfuric acid. Easy. It's easy. Sulfur is present in +8 oxidation state, which is not possible. There is one common name also for this acid. Do you know what is the name of this one? It is known as Marshall's acid. Marshall acid. H2 Marshall acid, oleum. Wait, it is not Marshall acid. Marshall's acid is H2S2O8. Pyrosulfuric oleum. And some common name is there for this compound.
So is it Cargos acid?
Carrose acid, yes. Yes, correct. It is Carrose acid. Yes. Carrot acid. Marshall's acid is H2S2O8. So it is known as carrot acid. Very good one, Afik. So these common names are also important. We will be having 3 common names here. So carrot acid is known as H2SO5. Okay. So how to make the structure? It is very simple. If we know the structure of sulfuric acid, we know the structure of peroxysulfuric acid also. It will be just like OOH. That's it. Like one OH, you just change it to OOH. Fine. Okay. But you know what is important? These are not important. The other 2 examples, which are where the structure is also important, which is this one, H4P2O7. What is this? Pyro. Pyrophosphoric acid it is. Pyrophosphoric acid it is. You add 1 oxygen here. Yeah. When we are adding 1 oxygen, it will become H4P2O8. And what is the name of this? This is now known as peroxy pyrophosphoric acid. Like whatever the compound you are having, you just add peroxy before that. Okay, oxidation state is 16, 12 plus 6, which is not possible, right? That is why there is peroxy linkage. So to represent that peroxy linkage, we are using that peroxy in the name of it. Peroxy pyrophosphoric acid. Okay, let us have the next one. This is important. H2S2O7. What is it here? It is pyrosulfuric acid. Pyrosulfuric acid. So when 1 oxygen is added here, it will become H2S2O8. H2S2O8 it will be having, right? And the name will be peroxy pyrosulfuric acid. Peroxy pyrosulfuric acid it will be having. Right? This is pyrosulfuric acid. Okay, fine. Correct? Is there any doubt up to here? So 3 prefix and 2 suffix we have done. 2 suffix are just like it is not even to add in the list. What is that? Ecanus. Maximum oxidation state is there, ec acid. Maximum -2, or we can say when 1 oxygen is removed from ec acid, it will become us acid. 3 prefixes what are important is pyro, hypo, peroxy. Pyro will become when we will just do twice of any oxyacid. We remove water from there. Resulting oxyacid will be known as pyroacid. And dye also you can use. And then if we are having hypo, then hypo can be used in 2 scenarios. If the oxygen is removed from us acid, then it will be known as hypoous acid. Second scenario is pyroic acid you are having. You remove 1 oxygen, you will be having hypopyroic acid, right? And the last one is peroxy, which is very simple. When oxidation state is more than maximum, this also I can say. Central atom oxidation state is more than maximum, then what the name will be using? Peroxy. We'll be using peroxy prefix in that case. Okay, fine. Correct. So now the last one we are having is meta. 4th one, meta. 4th one is meta. Metaic acid. Specifically, we can say it metaic acid. What is metaic acid here? What is metaic acid? Let us see. So there was a Mata in our class who was very thin. So we used to say, by drink something, water, you look very less of everything in your body. So you just have some content in your body. So which is lesser in something. So for example, if we are having a ic acid and then we are removing water from here, then the resulting oxyacid is known as metaic acid. Resulting oxyacid is known as metaic acid.
Metaic acid, right? So story is real or fake, it doesn't matter. The thing which matter is we should remember this name. Ic acid you are having, we are directly removing water from here, right? And it should have, like, if the oxy acid is formed, then we will be using the name as metaic acid. For example, and the 2 points are important for the metaic acid: exist in cyclic form, like they will always exist in cyclic form only, and does not exist in monomer, does not exist in monomeric form. Like either it will be dimer, trimer, tetramer, pentamer, like that. It won't be monomer. Example, let us take the example. Suppose we are having S3PO4 here. What is that? Phosphoric. If we remove water from here, what it will be becoming? It will be becoming HPO3. Now this HPO3 molecule will not exist independently. Like HPO3 does not exist, but its dimer, trimer, those can exist, right? And this is known as metaphosphoric acid. Metaphosphoric acid. Suppose, let us say N.
But we have meta-hypoic acid.
No. Meta is used only for normalic acids. Normalic acids only, right? It is not used for us. It is not used for hypo, only for ic acids. Let us take the value of NH3. Then how the structure will be forming? N value is 3, then HPO3 whole thrice we are having, right? HPO3 whole thrice. What is the oxidation state of phosphorus here? We cannot find, right? The thing is, you either you make it, you write it complete. It will become S3 P3O9. Then you find 18 15 plus 5. It is coming as plus 5, which is equal to maximum. Phosphorus has 5 valence electron. It is coming as plus 5. So when it is equal to maximum, there is oxy linkage, right? So, or you can remember this in the meta-acid cyclic form, you will be having oxy linkage in the structures.
Sir, it can be less than 5 also, right?
In meta, it won't be less than, because they are ic acids. So when they are ic acid, oxidation state will be equal to maximum only.
Okay.
So how we'll be making the structure? Very, very easy. What you have to do? How many phosphorus are there? 3. Like they are the central atom. You have to write that. And we have to make the structure as cyclic. So you put one oxygen in between 2 phosphorus atom. Right? Okay, fine. And then how many oxygens are still remaining? 6. And in the oxy acid, let me speak. In the oxy acid of phosphorus, there will always be double bond O, right? Double bond O will always be there. Double bond O will always be there, right? In the oxy acid of phosphorus, we have to make double bond O. Now, 3 hydrogen and 3 oxygens are there. So we will be making one OH with all the phosphorus, right? So now this is trimetaphosphoric acid. Trimetaphosphoric acid. Like we have to write how many phosphorus are there. So it is trimetaphosphoric acid because number of phosphorus is 3 here. So can you make, if the value of N is 4, and can you write the name for that? If the value of N is 4, you have to draw the structure and you have to write the name also. Okay. If the value of N is 4, beta, then it will be HPO3 whole 4, right? And what we have to do? We have to write 4 phosphorus atom. And then we have to put one oxygen in between them. Okay. And then always P double bond O. And I think remaining oxygen and hydrogen, you make one OH bond with all the phosphorus. And the name is tetraphosphoric acid. Have you understood here? Have you made the same? tetraphosphoric acid. Have you made the same structure?
Yes, sir.
Ovia?
Sir, I just
Yes, sir.
changed the orientation to
Huh?
like ऐसे square बनाया है कि
This-
diagonal थोड़ा.
Uh-huh. Like if you writing phosphorus like that, whatever the way, like it, there is nothing like geometry here. We are just talking about the type of bond. And they can ask how many POP linkages are there. So answer is 4. POP linkage are 4. How many PP linkage is there? 0. How many POOP linkage is there? 0. So there are oxy linkage only. How many oxy linkage? 4.
Sir, I have a doubt.
Yes.
So will it not be tetraphosphoric acid?
Correct. Tetrametaphosphoric acid. It will be tetrametaphosphoric acid. Tetrametaphosphoric acid. Okay. And then we are having, next one we are having is N is equals to 5. No, not N is equals to 5. Another acid, another meta acid. S3BO3. There are only 2 oxy acid. For them, meta form will be existing. If it is S3BO3 and we are removing one oxygen from here, it will become HBO2. Right? It will become HBO2. And what you have to do here, HBO2, when water is removed from here, water. This was boric acid, and this will become metaboric acid. Metaboric acid. And we have to write N here because it will be existing in the dimer or trimer form. So suppose, let us take the value of N is equals to 3. Value of N is 3, then it will become HBO3 whole thrice. The boron will be the central atom. Boron, boron, boron. This will be the central atom. And now we can see how many oxygens are there. 6, 9. 9 oxygens are there. HBO2. It was HBO2. HBO2 whole thrice, right? So how many oxygens are there? 6. So one oxygen you will be putting in between 2 boron atom. And now we can see 3 oxygen and 3 hydrogens are there. So one OH bond, and boron makes 3 bond only. Yes. So this will be trimetaboric acid. Right. Trimetaboric acid. Okay. So meta is very simple. You have to, how to make meta? You take ic acid, you remove water from that, you will be having metaic acid. Fine, beta. And the thing is, you cannot have metaic acid from any oxy acid. Like from all oxy acid, you cannot make. For example, suppose we are having H2SO4. If we remove water from here, what we will be having? We will be having SO3. We will be having SO3. And the thing is, SO3 is not an oxy acid at all. SO3 is not an oxy acid because there is no OH. When we are calling the oxy acid, when there is OH is linked with the non-metal, there is no OH bond. How we can call? It is oxide here. It is oxide. It is not hydroxide. So it is not oxy acid at all. So the thing is, metasulfuric acid is not existing. This is oxide, not oxy acid. Not oxy acid. Okay. It is oxide, not oxy acid. Okay. So the thing is, there is one name used to differentiate oxy acid from which metaform can be derived or not. What I'm saying here, for example, here phosphoric acid, you can make metaphosphoric acid. But sulfuric acid, you cannot make metasulfuric acid. So to differentiate them, we are using a nomenclature which is ortho, right? So orthonomenclature you can use for the oxyacid from which meta form can be derived. If meta form can be derived, you can use ortho. For example, orthophosphoric acid. If I am having S3PO4, what was S3PO4? Phosphoric acid. Can we derive meta form from here? Yes. So this is known as meta phosphoric. Wait, not meta, orthophosphoric acid. Orthophosphoric acid. Why ortho? Because from S3PO4 meta form can be derived. So we can use ortho also before its name. Right? It is not a nomenclature at all. It is just like we are using ortho. Where we are using? From where meta form can be derived. For example, S3BO3 is also there. That is boric acid. So you can call ortho boric acid. There won't be any question on ortho, don't worry. But the thing is, sometimes we see orthoboric acid they write. So why they are writing orthoboric acid? Because from boric acid, meta form can be derived. But you will never see orthosulfuric acid. Because from sulfuric acid, meta form cannot be derived. So you will never see orthosulfuric acid. Right? So these are the naming of oxyacids. And now I'm making a chart so that you can remember every name. Let us see. Just help me for the making the chart. Let us start with ic acid. Okay, we are having ic acid. We are starting with ic acid. And then if we remove one oxygen, or let us take, if we remove one oxygen from here, what will be having beta? We will be having us acid here. We will be having us acid, sir. And if we remove one oxygen from here also, then we will be having hypoous acid, sir. Hypoous acid. Right. And if we add one oxygen in acid, then it will be known as.
For hypoas, we have to multiply it into 2 and then remove water.
No. That was pyro. Peroxyic acid. Right. Peroxyic acid. Here, like we haven't done any molecule twice. They are just independent. Okay. Now, if you remove water from ic acid itself, then it will be known as metaic acid. Metaic acid, metaboric acid, metaphosphoric acid, like that. And then if you are making it twice and you are removing water, then this is known as pyroic acid. Okay, this is known as pyroic acid. Okay, and in the pyroic acid, if we are adding one oxygen, then this is known as peroxypyroic acid. Peroxypyroic acid. And if we are removing one oxygen from here, if you remember, that was hypopyroic acid, right? Second case of hypopyroic acid. Hypopyroic acid, right? Is there anything remaining, or everything is
Pyroas acid, right?
pyroas? Yes, that also we can do. We have to make it twice, and then we have to remove water. It will become pyroas. Okay, and we can write the examples for them also. For example, if we are having S3PO4, it will be S3PO3, phosphorus, hypophosphorus, metaphosphoric, peroxyphosphoric acid, H4P2O7, pyrophosphoric acid, H4P2O8, peroxypyrophosphoric acid, H4P2O6. This is hypopyroic acid, right? This is all the chart for the naming. So, like, is it clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Very good, yeah.
Sir, does this pyroic acid have any relation with pyruvic acid?
Pyroic acid is having any relation with?
Pyruvic.
No. That is a common name.
Okay.
Those are organic
Yes.
acid, carboxylic. Like they are organic acid. These are inorganic acids.
Yes.
If any relation is found, it is completely coincident. Okay. So will you be doing one question from oxy acid now?
Yes.
Okay. Just wait. Halogen acid, or we have to do halogen acids. Halogen acids. What are halogen acids? HClO4, HClO3, HClO2, HClO. These are halogen acids. And now what is the important thing here? Please see. The thing is, in the case of halogen, like if you remember, we have written except halogen acid. So why except? Let us see that. In the case of halogen, if you find the oxidation state, it will be coming as +7. This is +5. This is +3. This is +1. Right? These are the oxidation states. Now, if you write the name of this, it is maximum, right? Halogens have 7 valence electron in their valence shell. So +7 is the maximum oxidation state. So according to the naming, it should be ic acid. It should be chloric. If it is chloric, it should be chlorous. Then it should be hypochlorous. Right? And then what about this? Like we are not having any new name for this, no? For this compound only, we have to introduce a new nomenclature otherwise. Right? If we are following in that way, we have to introduce a new nomenclature for this compound only. And why to do that? Yeah? So instead of starting from ic acid, let us start from peroxy acid. This is perchloric acid. Then this is chloric acid. Then this is chlorous acid. Then this is hypochlorous acid. Right? Here we haven't introduced any new nomenclature. We will just keep this thing in our mind that here the name is used as perchloric, but there is no peroxy linkage. Only the name is perchloric acid because of the nomenclature series. Right? So this is perchloric acid. This is perchloric acid. What is this? This is chloric acid. What is this? This is chlorous acid. Chlorous acid. What is this? This is hypochlorous acid. Hypochlorous acid. Right, beta? Have you got it? Right. There is like perchloric acid, there is per or peroxy name, but there is no peroxy linkage because oxidation state is not more than maximum. We are just using the name per, but there is no peroxy linkage. Right. Similarly, if we are having HBrO4, HBrO3, HBrO2, there is nothing like we have to remember this. This is very simple. HBrO, right? What is that? This is perbromic acid here. Perbromic acid. What is that? Bromic acid. And then what is this? Sir, this is hypobromic, not bromous. Bromous acid. Then what is it? Hypobromous. Right. So is there any doubt in the halogen acid? For iodic also we can use periodic, iodic, iodous, hypoiodous. Right? It's simple, right? Is there any doubt?
No, sir.
Okay. Then solve this question. If you will be solving this question correct, then we'll be finishing our class.
So for halogen also we can use everything we use for those other ones, that oxy acid.
Pyro and all these things.
Yes, sir. Can we use meta, pyro?
Thing is, they are not existing. They are not existing. Like
Okay.
there is nothing like metachloric acid. Okay.
Okay.
Hypo prefix in its name. Number of acids which are having hypo prefix. Hypo. Okay. So can we see now?
So is it 4?
4. I think your answer is 4. Okay. We'll see. Vedant, what is your answer?
So just 1 more minute, I'm doing it.
Ovia, are you able to solve?
Yes, sir.
Okay. What is your answer, Vivani?
So 4.
4. Varun, your answer is 3.
Sir.
Ovia, what?
Three.
Ovia, have you
Sir,
solved?
I'm also getting 3.
Sir, I only got 3, sir.
3. Okay. Let us see. S3PO4 is phosphoric. So this is not our answer. S3BO3 is boric. That is not our answer. S3PO3 is phosphorus. That is not our answer. S3PO2. That is our answer. That is hypophosphorus. HClO3. HClO4 was perchloric. HClO3 is chloric. That is not our answer. HClO is hypochlorous. Yes. Right now, just now we have seen perchloric, chloric, chlorus, hypochlorous. This is our answer. HNO. If you remember, like HNO3, which we were started, HNO3 nitric, HNO2 nitrous, then HNO that does not exist, but that's dimer exists, which is known as hyponitrous. This will also be existing. H4P2O6. If we were having H4P2O7, from that is oxygen is removed, then it will become H4P2O6 only, and the name will be hypopyrophosphoric acid. Like there are 2 cases of hypo, na? So answer will be 4 here. Afik, you considered these 4 only?
Yes, sir.
Vedant?
Sir, I missed HNO wala.
Okay. Ovia?
I missed hypochlorous acid.
Vibhani?
Same, sir.
You also missed.
No, sir. Same. The one.
Very good. And Varun yaar, which one you missed?
The HNO I missed, sir.
कोई बात नहीं. One more question, huh? Easy है.
Sir, how was the paper of the other shifts?
Paper was easy in all the cases. Like paper was not a difficult one. For JEE mains, I think the preparation should be of different strategy here. Like sometimes student gets confused when they are taking both the preparation, like JEE mains as well as advanced. Then like they are not able to do the good things or the harder things, and for that like they just skip the easier part also. Like they are confusing in easier things also. So if you are focusing on mains, then it should be more based on the simple problem based. It should be more based on NCRT. It should be more based on PYQs. Like if you just prepare and then if you solve 2025, for your case 2024, 2023, these papers and the notes and some questions, these will be sufficient, more than sufficient enough to clear the JEE mains. It is not difficult. JEE mains is more about doing one thing again and again, right? JEE mains is about that, doing revising oxy acid, doing more questions on oxy acid. It's just like that. It is not like going in more detail, right? So like these simple questions, if we are doing, you will be able to clear it. The thing is, at the end of the syllabus, 12th exam, you just need to cover all these things. And if we are not doing a lot, then we will be able to cover these things. We will be able to revise these things, right? But the thing is, students do this book, that book, questions from that particular coaching institute. Then at the end of the syllabus, they are not able to extract something good from any chapter, right? So our sources should be limited, right? The most important thing is the notes always, and second is your module. That's it. At the end, PYQs. That's enough, right? It's not about getting a good rank in your coaching paper, which they are making the toughest. It is just about securing a good rank in JEE mains, which is not toughest, right?
Yes, sir.
Okay, solve this one. Question number 20. Except this one. Except this case. But you have to make the 20. You have to make this structure. Na? You can do that. Wait. You cannot do this here. Do this one. 18th is easy. Some part is still remaining. Not for oxy acid, for oxides. P4O6 is what? Oxide. It is not oxy acid. It is oxide. Yes, this one. Question number 52 is good. 52 is good one. Ovia, you won't be able to solve this. This is a part of previous class.
Okay.
The pair that contain two pH bonds in each of the oxy acids. Good question. Done?
Sir, it's single correct, right?
Yes, single correct. JEE mains.
Sir, I got an answer, but I'm not sure.
What answer you got?
A, sir.
Hmm.
Okay. What is your answer, Vibhani?
First, third.
First one.
Yes, sir.
Okay. And then Varun.
First one, sir.
Afik.
First one.
Yeah, very good. If you all are saying first one, then first one is the correct. It must be correct. S3PO2. S3PO2 is just like this. P double bond OH, H and H. And if you remember H4P2O5, this was the case where POP linkage was there. Right? POP linkage. So P double bond double bond O. And then one OH, one H, one H, one OH. So yes, we can see there are two PH bond, right? In H4P2O5, H4P2O6. So in this case, there were two structures existing. It was tri-basic and tetra-basic, if you remember. It is there in the notes. S3PO2, S3PO3. So it is wrong because of S3PO3 because it is just like this POH, OH, and H. There is only one PH bond, right? Same for here. So answer is 1. Correct. Go. Very good.
Okay, sir.
Okay.